Welcome you all in the lecture number 8 of Abstract Algebra MTL 6051. In this lecture we will going to discuss what is the center of group, what are the examples related to the center of group, and what is the centralizer of the group, and what is the relation between centralizer and center of group and center of group with the group. Okay, let us see what is the center of. Center of group is defined as follows. If G be a group, suppose if G is group, then center of group is denoted by ZG. What is G? G is group. And what is center of group? Center of group is denoted by ZG. Okay. And denoted by this, but how it is defined? It is containing all those elements of G. For example, G belongs to capital G such that G of X equal to xg, right? For all X belong to G. It means center of group containing all those elements which are satisfy the commutative property with other elements of the group, right? All collection of all such elements form the center of group. Whether ZG is empty? No, ZG cannot be empty. This cannot be empty. Why? Since E belongs to G and E of X is equal to X of E for all X belong to G. Therefore, at least one element E in the ZG. Therefore, ZG cannot be empty, right? Then, if ZG is non-empty, whether the ZG is group, ZG is group. If ZG is group, then ZG is the subgroup of the group G, right? But first we have to prove that ZG is group. Let us see. Let us see how we will prove ZG is subgroup of G, right? ZG is subgroup of G. Related to this, we already proved one theorem in the subgroup, that is, if AB belongs to ZG, this implies that AB inverse belongs to ZG. If this happens, then ZG is subgroup of G, right? For this, if we want to prove that ZG is subgroup of G, then we have to show this property, right? Let us start. Let us start the proof. Let A and B belongs to ZG, right? Then what is AX? AX is equal to XA, right? And what is BX? BX is equal to XB. And this property holds for all X belong to G, right? By definition of center of group. Then check this one, right? Multiply, operate B inverse from the left side as well as right side. That is B inverse BX, B inverse is equal to B inverse EXB, B inverse. Then what happened? This B inverse B is identity. Then this is EXB inverse, and this B inverse is identity. This is B inverse X. This is equation number 3. And this one is equation number 1, and this is equation number 2. Equation number 1, equation number 2. And this property, this relation is equation number 3, right? And this shows that B inverse belongs to ZG, right? Now consider AB inverse EX. What is this? This AB inverse can be written as AB inverse X. Why? By associative law, right? Since A, B inverse and X are the element of G, therefore using the associativity, A, B inverse X, and this is equal to A, and B inverse X can be written as AB EXB inverse by using equation number 3. And this can be written as, again apply associativity, AXB inverse. Then what is AX by equation number 1? This is EXA B inverse, and this can be written as XAB inverse, right? Finally, what is B obtained? AB inverse X is equal to XAB inverse. It means this AB inverse commutative with all, and this relation is true for all X belong to G. It means AB inverse is the element of ZG, right? Since AB belong to ZG, this implies that AB inverse belong to ZG, and hence ZG is subgroup, right? Hence ZG is subgroup. Now, if ZG is abelian subgroup of G, right? So that, sorry, what is the problem? Problem is that we have to prove that ZG is abelian subgroup of G, right? Whether the ZG is abelian subgroup of G, let us check. Let A belongs to ZG, right? Then A of X is equal to X of A. See, sorry, AX is equal to XA. AX is equal to XA for all X belong to G. If X be take B, then what is AB? That is BA. And this AB is equal to BA for all AB belongs to ZG, right? For all AB belong to ZG. And this relation shows that ZG is abelian. ZG is abelian, right? Therefore, ZG is always abelian subgroup. Therefore, this is abelian and subgroup. This is abelian subgroup of G. ZG is always abelian subgroup of G, right? Now see one example. Let us consider quaternion group Q4. What is Q4? Plus minus 1, plus minus I, plus minus j, and plus minus k. What is z of Q4? What is center of Q4? Right? Center of Q4, which element is commutative, satisfy the commutative law with the other element? Of course, identity is here, no doubt. Identity commutative with every element of Q4. And which other element in ZQ4? That is minus 1, since minus 1 into I equal to I minus 1. It means minus 1 satisfy commutative law. Minus 1 j, j minus 1. Minus 1 minus I equal to minus I minus 1. Right? Similarly others. It means minus 1 k is equal to k minus 1. And minus 1 minus k equal to minus k minus 1. These all are equal. It means minus 1 satisfy commutativity law with other elements. Then minus 1 is also here. Right? Check whether I also belong in ZQ4. See, for I dot j equal to j dot I? No, I dot j does not equal to j dot I, right? Then I does not satisfy commutative law, and similarly j also not satisfy commutative law, right? Similarly k also not, and minus I minus j minus k. Then z of q4 containing only two elements, that is 1 and minus 1. These two elements holds the relation that ax is equal to xa for all x belong to G. Right? These two elements holds commutative law with all element of Q4. Right? Hence ZQ4 is equal to 1 and minus 1. Right? And check this. This is subgroup as well as abelian. Therefore, it is abelian subgroup. Right? Which we already proved. Now see, if G is abelian, then suppose for which we are calculating the center of group, that group is already abelian, means G is abelian. G is abelian. If G is abelian, then AB is equal to BA for all AB belong to G. Then what is ZG? ZG is whole G, right? Since all element of G already satisfy commutative law, and ZG containing all those elements which satisfy this commutative law, then ZG equal to G. If G is abelian, then ZG equal to G. Right? What is Z? Z with respect to plus is abelian group. Then by this relation, Z of set of integer is equal to set of integer, and Z of Q is Q, since Q is also abelian group. Set of real number is abelian group, therefore Z of R is R. Z of C is C. Z of Zn is Zn. Right? Similarly, other examples also. But the converse of above statement is true or not? Right? It means if Zg equal to G, then this is abelian. Sorry. If Zg equal to G, then whether G is abelian? Yes. Answer is yes. If Zg equal to G, then this G is abelian. Why? See left hand side. What is Zg? Zg is always abelian. And what is G? G equal to Zg. Therefore, G is also abelian. Right? If G is cyclic, then Zg equal to G? Yes. If G is cyclic, then we know that every cyclic group is abelian group, and this is abelian. Right? Every cyclic group is abelian group. The G is cyclic, then this is abelian. And every abelian group satisfy this law. Zg equal to G. Hence Zg, if G is cyclic, then Zg equal to G also. Right? Now, if Zg equal to G, then G need not be cyclic. If Zg equal to G, then G is abelian. Okay. Right? If Zg equal to G, then G is abelian. And converse is also true. Right? If Zg equal to G implies that G is abelian, and if G is abelian, then Zg equal to G. But if G is cyclic, implies that Zg equal to G. If G is cyclic, then Zg equal to G. But whether the converse is true? No. Right? If Zg equal to G, then G may or may not be cyclic. Right? See the counter example. Z4 cross Z8. Right? This is group. Right? This is group. And what is Z of Z4 and Q8? Sorry, Z8. Right? This is Z4 Q8 Z8. Then Zg, if suppose this is G, is equal to G. Right? Zg equal to G. But this group is not cyclic group. Not cyclic group. Since no element in Z4 cross Z8. What is Z4 cross Z8? Z4 cross Z8 is equal to 0, 1, 2, 3 cross. What is Z8? 0, 1, 2, 3, 4, 5, 6, 7. Right? Then this is total 32 element. It is set of 32 element. In these 32 element, no one element, not a single element which can generate all these 32. Right? Therefore, this is not cyclic. But Zg is equal to G, means Z of Z4 Z8 is equal to Z4 Z8. Right? But converse is not true. Now, what is Z of K4? What is K4? K4 is abelian. Right? We know that K4 is abelian group. K4 is abelian group. Why? E A B C E A B C E A B C A of A is identity, A of B is C, A of C is B. B of A is B, B of A is C, and B of B is identity, and B of C is A. And C of E is C, C of A is B, C of B is A, and C of C is E. Check. First row and first column equal. Second row, second column equal. Third row, third column equal. Fourth row, fourth column equal. It means this K4 is abelian. Right? This is abelian group. Then what is its center? If this is abelian group, then its center is whole group. Z of K4 is equal to K4. Right? This one. Similarly, what is Z of S1? Yes, what is S1? S1 containing only identity permutation. Then Z of S1 is S1. Now, what is Z of S2? S2 is also abelian group. Then this is S2. What is Z of Sn? For all n is greater than or equal to 3, Z of Sn is only identity. Right? What is Z of A1? Identity. Z of A2 is A2, Z of A3 is A3, and Z of An. What is Z of An? Right? This is identity for all n is greater than or equal to 4. Right? This you can verify. This is homework for you. Now, what is Z of Z2 cross D3? What is Z2 cross D3? Right? G1 cross G2. We already proved that this is group, and this containing this type of element ordered pair AB, where A belongs to G1 and B belongs to G2, and this AB and CD is equal to ACBD. With respect to this operation, this G1 cross G2 is group. Right? This result we already proved in our previous class. Now see, apply this result here. What is G1? G1 is Z2. What is G2? G2 is D3. Z2 cross D3, that is AB. A belongs to Z2 and B belongs to D3. Okay. Then what is the relation? ABCD is equal to CDAB. Why? Since we are evaluating center of Z2 cross D3. Right? Then what is this? By this definition, this is ACBD. This is ACBD. And what is this one? Using this definition, this is CA and DB. CA, DB. Okay. Right? Then what is AC? AC equal to CA. Right? Two ordered pair are equal, means x1 y1 equal to x2 y2. It means x1 equal to x2, y1 equal to y2. AC equal to CA for all C belong to Z2, and BD equal to DB for all D belong to capital D3. Then AC equal to CA for all C and BD equal to DB for all D. Right? Then this can be written as AB. A belongs to Z of Z2. This is the definition of Z of Z2. And this one is the definition of Z of Z3. Right? Then A belongs to Z of Z2 and B belongs to Z of Z3. Therefore, the Z of Z2 is equal to Z of Z2 cross Z3 is equal to Z of Z2 and center of Z2 cross center of D3, right? What is center of Z2? Center of Z2, Z2 containing only two elements, 0, 1, and this is abelian. Therefore, Z of Z2, center group of Z2 is 0, 1, right? Since it is abelian, therefore it is whole Z2. And what is D3? D3 is non-abelian group, right? It is non-abelian group. Then what is center? Its center is R0. This is also homework for you, right? You can verify all 6 elements, only this element in center of D3, right? This is R0. How many element here? 2 element, right? 0 and 1. And how many element here? R0. And Cartesian product is 0 R0 and 1 R0. Okay, this is the center of Z2 cross D3. Now see, what is Z of Z4 D4? Z of Z4, that we already proved that. What is Z of G1 cross G2? Right, this is Z of G1 cross Z of G2. We will prove it, right? This theorem. We will apply this theorem here. Now, Z of G1, Z of G2. What is Z of G1? G1 is Z4. This is Z4 cross Z of D4. Okay. What is Z of Z4? Z of Z4 is 0, 1, 2, 3. Right? This thing. Since Z4 is abelian, therefore Z of Z4 is Z4. What is Z of D4? That is R0 and R180. Okay. Right? Then this is 0 R0, 0 R0, 0 R180, 1 R0, 1 R180, 2 R0, 2 R180, 3 R0, 3 R180. Okay. This is the center of Z4 cross D4. This is Z4 cross D4. Now, we have to prove that center of G1 cross G2 is isomorphic to center of G1 cross center of G2. Right? There is no difference between this and this. Okay. Right. We will prove it similar way, just like previous example. Let center of G1 cross G2 is AB belongs to G1 cross G2. Means all those elements of G1 cross G2 of the type AB which satisfy commutative law with the other element of G1 cross G2 like CD. Right? Right? AB CD. AB CD is equal to CD AB. Right? For all CD in G1 cross G2. Then by the operation, this AB CD is equal to CD AB. Then what is this? This is ACBD. Right? What is this? CADB. Then ACCA. ACCA are equal. And BDBD, DB equal. Okay. This is for all C and this is for all D. If this is for all C, then this is ZG1, sorry. Right? And B belongs to Z of G2. And this is Z of G1 cross Z of G2. Okay. Now, what is the order of center of Z4 cross D4 cross Q4? By the above theorem, we prove that this is isomorphic to this one, Z of Z4, D4 and Q4. This is isomorphic to Z of Z4, Z of D4 cross Z of Q4. Okay, Z of Z4, Z of D4, Z of Q4. This is isomorphic to this one by the above theorem. Right? Then what is Z of Z4? Z of Z4 is 4. Order of Z of Z4 is 4. Right? Since Z4 is abelian, therefore 4. What is Z of D4? Z of D4 is 2. That is R0 and R180. And this is 2. And what is Z of Q4? Z of Q4 we already evaluated, that is 1 and minus 1. This order is also 2. Then 4 into 2 into 2 is 16. right? And generalization of the above theorem says that center of G1 cross G2 cross Gn is equal to isomorphic to, not equal to, it is isomorphic to center of G1 cross center of G2 cross center of Gn, right? This is the generalized result. Okay. Now see another example. If G is equal to GL to Z2, S3 and Z3, then what is the order? Then what is order of Zg? Means order of Z of GL to Z2 and S3 and Z3, right? By using above theorem, this thing can be written as center of GL to Z2, first one, cross center of, right, not this one, this is center of S3, and this one is, sorry, this one is center of Z3, center of S3 and center of Z3. Okay. Now what is GL to Z2? Only one element which satisfy commutative law with the other element, that is identity, right? Then order of this one is 1. Okay. And what is Z of S3? I already shown you in the example. Z of S3 is only identity element. Then this order is also 1. What is Z of Z3? Since Z3 is abelian, therefore Z of Z3 is whole Z3. And what is the order of Z3? Z3 is 3. Therefore 1 into 1 and into 3. Right? This is equal to 3. Then what is Z of Zg? What is Zg? What is Z of Zg? See, what is, if G is abelian, then what is Zg? Zg is equal to G. If G is abelian, right? If G is abelian, see, what is Zg? This Zg is abelian. Then this, please wait 1 minute. What is this Zg? Zg is abelian. Then what is this Zg? Right? If Zg is abelian, then Z of Zg is also Zg. Now this Z of Zg is Zg. Now this Zg of Zg is equal to Zg. It means this answer is Zg. Okay. Now come to the centralizer of an element. Right? Center of an group, but centralizer we evaluate for any element of the group. What is that? If G is any group, suppose G is any group and A is element of G, then centralizer of this can be denoted as Ca. What is centralizer? It is denoted by Ca, and it containing all those elements X belong to G such that X of A is equal to Ax. Right? X is equal to Ax. It means centralizer of any element from the group G which can satisfy commutative law with that element only. For example, if we evaluated C of A, then C of A is all those elements of G, that is of the type X belong to G, and this X satisfy commutative law with this A. It means Xa is equal to Ax. Then such collection of X is known as centralizer of A. Right? Now see, whether the Ca is subgroup of G, again we have to prove that if AB belong to Ca, then AB inverse belong to Ca. Right? If we are able to prove this, then only we can say that Ca is subgroup of G. We can only say that this is subgroup of G. Let us start from here. A and B. Let A and B belong to Ca. Then again, right? Let us assume that X, Y are A, B in. Since we are using A here, that's why we change this element, not A and B. Since we are calculating centralizer of A, that's why we are using XY. Otherwise If you are using centralizer of x, then you can use here AB. Check the notations carefully. See, let xy belong to CA. Then by definition of CA, xa is equal to AX and ya is equal to AY. Right? Okay. Again, using this one, second, y inverse ya y inverse equal to y inverse ay y inverse, right? And this one is identity. This is ay inverse and this is y inverse a, and this one is identity. This is equation number 3. Again, start from here. xy inverse a, right? Assume that xy inverse a. Apply associative law. This you can write by this. Why? Since xy inverse a all are the element of group G, then this can be written as x ay inverse by equation number 3. This is using equation number and 3, and this one is by associative law. By associative law. Okay. Again by associative law. Associative law. xa y inverse. This xa can be written as ax using 1. Using 1. And again by associative law. Again by associative law. This is axy inverse. Now xy inverse a is equal to axy inverse. It means xy inverse is centralizer of a. Right? xy inverse belong to centralizer of a. Since xy inverse is the element which satisfy commutative law with a. Right? Hence CA is subgroup of G. Okay. Next, CA need not always be abelian. Why? Since C of R0, what is center of R0? Center of R0 is D4. Right? Center of R0 is D4. Every element of D4 satisfy commutative law with R0. That is, centralizer of identity element is whole group, whether G is abelian or not abelian. Right? It means centralizer of any element it is subgroup, but it is not always be abelian. It may or may not be abelian. What is the relation between center of group and centralizer of an element? If we evaluate centralizer of all element of group and take intersection of centralizer of all element, then we find the ZG. See how we prove it. We know that if A two sets are equal, for this we have to show that A is the subset of B and second one B is the subset of A. These two results will give us A is equal to B. Now see, what is CA? CA, we know that all the element of G which commute with A. Okay, that is centralizer. What is ZG? All element of G which satisfy commutative law with every element of G, means which commute with every element of G, that is center of group. We have to show that these two are equal. Now let X belong to ZG. Then X of A is equal to AX for all A. Okay, by definition. X, this property says that this only, not we are not using this one. This only says that X is in centralizer of A. Right? X is in only this one says that X is centralizer of A. And this says that X belong to centralizer of every element of G. This one for all A belong to G. It means if X is in centralizer of every element of G, then X is also in intersection of centralizer of A. Right? It means X belong to centralizer of A for all A belong to G. X belong to ZG and X belong to this also. It means ZG is subset of this first equation. Right? Now let X belong to intersection of centralizer A. Let X belong to intersection of centralizer of A. Then X belong to CA for all A belong to G. If X belong to centralizer intersection of centralizer of A, right, for all A belong to G, it means X belong to CA for all A belong to G. X belong to CA. This says that X commute with A. X is equal to AX. That is for all A belong to G. And this says that this whole thing says that X is in center of G. If X belong to this and X belong to center of G, then this intersection of centralizer of A for all A belong to G is the subset of ZG, right? Then from first and second says that ZG is equal to intersection of centralizer of every element of G. Okay. Okay. We will stop here. In next class, we will see some problems related to centralizer. Okay. Thank you.